All right, well, you've had a day to work on this idea of bringing time in calculus into problems and setting these problems in motion. So we're going to revisit that today. We're just going to keep practicing how the rates of change are related to each other, how if you change one rate, it affects the other rate. We're going to look more at specific moments in time with more numerical examples today. So we're going to start with high-speed chase. All right, so let's suppose that we have a suspect being chased by law enforcement, and the suspect has turned the corner and the officer is still chasing them. Now, there are some numbers here that are going to be distracting to you right away. I need you to, again, ignore those numbers as rates. Focus on the geometry of the problem first. Okay, so we've got a corner going on here, and the police officer is heading that direction, and here is the suspect, and the suspect has, turned the corner and is going away from the police officer. And then we've got the distance that is measured between them. All right, so let's look at the geometry of this. This is a right triangle, and so I'm going to give the geometry of this x, y, and say z. So the geometry of this problem is the Pythagorean theorem. Okay, we know that x squared plus y squared equals z squared, the distance between the police officer and the suspect. Now, this is the geometry of the problem. The calculus puts this in motion when you take the derivative with respect to time for each variable. So that's my next step, is calculus. Here's geometry. Now I'm ready for my calculus step. So the derivative of x squared is 2x, and then times the time differential of dx dt. That's the rate at which the x side of the triangle is changing. The x side of the triangle is getting longer as the suspect goes farther away. Then we've got the derivative y squared, so 2y, and the time differential to show that is changing. And so that is the changing side of y. And that side is actually getting smaller as the police officer gets closer and closer to the corner. And then we've got the derivative of z, so 2z times the time differential dz dt. So first we do our geometry, and then we do our calculus, and we put this in motion. After we've done those two things, then we can go back to the values and we can plug them in. So the officer is going 80 miles per hour. That represents the side of the triangle for the officer, which is the y side. So that is going to go in here for the rate and the time. But we know that it's getting smaller because the side of the officer's side is getting smaller as the officer gets closer. Like the triangle is changing, right? The triangle, as the officer moves down the road, the suspect also moves farther, and so the triangle would then change and look like that. So the suspect side is longer, but the officer side is shorter as the two keep moving. So that means what we put in here is negative because that side is getting shorter. Then we have 20 miles an hour, which is talking about the distance between them. So 20 miles an hour is going to be going in for dz dt, but that's a positive number because the hypotenuse of the triangle keeps getting longer. So that would be positive. And then we have our 2x dx dt over here, which we don't know. The question is asking about the speed of the suspect. So that's the x side of the triangle. So we want to get this term alone. So we're going to simplify and move some things around. So I'll have 2x dx dt minus 160y equals 40z. And then we want to get that dx dt alone by adding and dividing. So I'm going to add 160y to both sides, and then I'm going to divide. So I'll have 2x dx dt being equal to 40z plus 160y. Then I'm going to divide both sides by 2x. That means I'll divide each term by 2x. So I'll end up with dx dt alone being equal to, okay, we'll reduce, we get 20z over x. And when I reduce, I get 80y over x. And that is the final answer now that you have dx dt alone. And this is going to be measured in the units. X is measured in miles and t is measured in hours. So this is miles per hour, or mph. All right, so we've got things in motion. The moment we specify a specific time value, okay, we say 5 minutes or give a specific time value, all motion stops. It's like a freeze frame. It's that, like we talked yesterday about the burst of pictures on your camera, but you pick the one moment that you want. So as soon as you pick a time value, all motion now stops and you've frozen this image. So we want to do that at the very, very end. So let's get these blanks. At the instant you specify a particular value for time, all motion stops. Okay, so words like what to look for is at the moment of, or when the value of time is. Those are cues that you're going to plug in a time value. But you want to make sure you do this last, okay, at the very, very end. Save that time value for the very last thing you do. It's going to be so tempting to want to put time in earlier, but I can't give you strong enough advice to wait on that until after you've done your geometry, after you've done your calculus, after you've done all the moving around that you need to do. The very end, plug in your time values. So we're going to go back to a problem we started the other day, and that was the spherical soap bubble. Okay, so this is a bubble, right? 3 dimensionals. The geometry of this was the volume. The volume of the soap bubble is 4/3 pi r cubed. Okay, that's our geometry. Our calculus is dv over dt equals 3 times 4/3 pi, which are constants, r squared times the differential of dr dt. We can reduce the 3's, and then we can look for plugging in values. So the values that we see are the value of 10, and it's got a cubic centimeters and a seconds on it. So that's a unit for volume and a unit for time. So that's going to be plugging in here. So that is the rate. We also have the value of 2 centimeters. So this is an additional value that we didn't have before. So this is the value that's going to measure the radius. At the moment, the radius is 2 centimeters. It doesn't have a time value on it yet, so that's not going in for dr dt. It's just going in for r. You can't go in for a dr dt unless you have time. So let's see what we've got. And the 10 is going to be positive because we're blowing air in. If we were sucking air out, it would be negative. So this is a positive 10. Equals 4 pi, and then 2 goes in for time squared, and then we have dr dt. So in order to answer the question is how fast will the radius be changing? And that will be answered by getting dr dt by itself. So when we divide, we'll have 10 divided by, we end up with 16 pi. That equals dr dt. So when we reduce the 10 and the 16, we have 5 over 8 pi. And the units for that are the units for the radius, which are centimeters, and the units for the time, which are seconds. So now we have a numerical answer. We've never had a numerical answer before. We've had, our previous answer had variables in it still, right? We had units, but we still had variables. Okay, this answer is all numbers because we had all of the values. So I want to do the same thing with the high-speed chase. Okay, so remember that we started with x squared plus y squared equals z squared as our geometry. And our calculus got us to 2x times dx dt plus 2y times dy dt equals 2z times dz dt. So that's the calculus part of it. Now you can look to plug in some numbers. So we know the officer was going 80 miles per hour, but that was negative. So that was where we had our negative 80 put in. We know the distance between them was increasing, so positive, at a rate of 20. Okay, that went in here. We also have some additional information we didn't have before. Now we know that the officer is 1/4 mile from the corner and the distance between them is 1/2 mile. So I'm going to redraw some geometry over here. Okay, and we're freeze framing now this moment. We know that the officer is 1/4 and we know that the distance between them is 1/2. That left x down here. I should be able to figure, so this was the y, this was the z. I should be able to figure out the value for x using the Pythagorean theorem. So x squared plus 1/4 squared equals 1/2 squared. So that's x squared plus 1/16 equals 1/4. So if we subtract 1/16, we get 3/16. So x is both the plus and the minus square root of 3/16. But we only need the positive one right now because we're on the positive side of the origin. So now not only do we have a 1/4 to go in for y and a 1/2 to go in for z, so let's get those in. The 1/2 goes here, the 1/4 goes here. We also now have the x value of rad 3/16. And the only thing left that's a variable is dx dt, which represents the changing on the side of the x, which is the suspect side. So that answers the question, how fast is the suspect going? That's going to be the dx dt answer. So we just need to now simplify and move some things around. So we've got 2 rad 3/4, because the square root of 16 is 4, dx dt. And we can reduce the 2 and the 4. Then we've got minus, so 2 times 1/4 times 80 is minus 40. And then 2 times 1/2 times 20 is 20. So we should be able to solve this by reducing and adding 40 to both sides. Okay, so I'll also add 40. So what do I have? I've got rad 3/2 now, dx dt, equals 60 when I add. And then I multiply by the reciprocal of rad 3/2. So I'll multiply by 2 over rad 3 and by 2 over rad 3. So dx dt is 120 over rad 3. And the units for this, I need the unit for the x, which is in miles, and then I need the unit for the time, which is in hours, so miles per hour. So again, now I ended up with a numerical answer today rather than just variable answers. Let's practice it again. From 200 meters away, an observer, a person, watches a hot air balloon rising. The angle between the balloon and the person who's watching it is changing or increasing at 10 degrees per minute. The moment the balloon is 1,000 meters high, okay, so at the moment, that's that freeze frame here, find the speed of the balloon. Well, let's do our geometry first. All right, so I've got my person over here, 200 meters away, watching the balloon. You know what, and I'm not going to use the number 200 yet. Okay, so I'm going to use x. And watching the balloon up here and I'm going to use y. And they also mentioned the angle, so I need angle. Okay, we call that the angle between the balloon and the observer, the angle of elevation. So actually, I'm not going to need geometry, I'm going to need trigonometry this time. This is an opposite over adjacent situation. And so this is going to be, if you remember your SOHCAHTOA, this is a time for tangent. So my trig is that the tangent of theta is the opposite y value over the x value. So this is my trig. Now I'll do my calculus. My calculus is where I take the derivative and I bring time into the problem. So when I take the derivative of tangent, and technically there should be parentheses, I have to do the outside first and then the derivative of the inside. So you got to remember the derivative of tangent from first semester. The derivative of tangent is secant squared, but leave the inside alone. And then take the derivative of the inside, which is when time comes in, because we're treating theta just like a variable. On the other side, we need to take the derivative of y over x, which means you need to remember the quotient rule. Yesterday we talked about the product rule. Today we have to remember how to do the quotient rule. So the quotient rule starts me out with x, which is on the bottom, times the derivative of y with respect to time. And then this is a subtraction, and then y times the derivative of x with respect to time. And then the whole thing is over x squared, so the good old quotient rule that we have. And that's the calculus step. After I've finished my trig/geometry and my calculus, now I can start plugging in some numbers. All right, so from a distance of 200, that is the value of x. So I'm going to put 200 in for x there, and I'll put 200 in for x in the denominator, square it. Okay, the angle, let's see what else we have. We have the balloon is 1,000 meters high. That's the value for y. And so I'll put that in for y for 1,000. Okay, all right, next we also have the 10 degrees per minute. That has both a theta measurement and a time measurement. So that's going to be my d theta dt, and it's increasing, so it's positive. So I'll put 10 in here. A couple other things we have to infer. I'm going to try and erase, I'm going to get rid of some of my arrows here just so that I can declutter what I had going on. Okay, so remember, we know that x is now 200, and we freeze framed it where y is 1,000. So we need to figure out the hypotenuse of this triangle for 200 and 1,000. So we need a z. So we'll do a little more Pythagorean theorem. So this is my scratch work here over the sun side. So x squared plus y squared equals z squared. So 200 squared plus 1,000 squared equals z squared. That's 40,000 plus 1,000,000. So z is the square root of 1,040,000. Just leave it like that, that's fine. Okay, so now we know this. How can we find secant squared from that? Well, remember, secant is the reciprocal of cosine. And what would cosine be in this picture? Cosine of theta is SOHCAHTOA, it's adjacent over hypotenuse. So secant must be the reciprocal of that. over 200. And if I want to square that then, so it would be the reciprocal over 200 squared. That's the secant value that went in there. So what's left? I've got some parentheses here that I still need to figure out. dy dt, okay, this one, that represents the balloon changing, the side that is on the balloon. dx dt represents the side where the person is standing and how that one is changing. In this particular situation, the person is standing still. The balloon is moving, but the person is not moving. And so since the person is not moving, we can put 0 here because they are motionless. So the only thing that didn't get plugged in was the dy dt, which is the motion of the balloon. Let's see, I'll do that in red. Okay, whew, that was a lot. So now we're just going to clean this all up and simplify. Okay, we may need to cross multiply a little bit. So on the left side, I'll have 1, 0, 4, 0, 0, 0. Oh, there we go. That's all my zeros. So I squared it and I multiplied it by 10 over 200 squared. And on the other side, the 0 is going to knock this out. So I'll have 200 times dy dt over 200 squared. And again, I can reduce my 200 with the 200 squared. So that just leaves me with 200 in the denominator. And now I can cross multiply. So this now becomes an algebra problem where we cross multiply that way. And then we'll have 200 squared times dy dt equals 10,400,000 times 200. And then we can divide both sides by 200 squared to finish the problem. So we can reduce both of these, and we can reduce this 200 with that square. All right, so get rid of that, and we've just reduced. All right, so our answer is 10,400,000 divided by 200. So we can simplify that by reducing the 2's, and we end up with 502,000. The units on this, okay, now let's remember what we're measuring. Okay, the units are y is measured in meters and time is measured in minutes. All right, so that was, again, pretty big, beastly problem that you had to have. Everything comes together. You got to know your trig. You got to know your quotient rule. Got to know your Pythagorean theorem. Got to be able to cross multiply. All coming together in these single problems. All right, let's look at a cylinder. We've got a lot of numbers in a cylinder. Container, it's 200 centimeters tall, radius of 5, filled with ice cream. Okay, now we want to ignore those numbers and just start with what we know about the geometry of a cylinder. So volume is pi r squared times h. So there's our geometry. Our calculus will be the derivative, and we saw this yesterday. The derivative dv dt, pi is a constant, and then when you take your derivatives, it's one at a time. right? Take the derivative of r squared, that's 2r, times the differential of dr dt, and then h doesn't change, h stays alone. And then plus for the product rule, pi times r squared being alone, and the derivative of h, dh dt. Then we can start filling in some numbers. Okay, a container is 20 centimeters deep, and the radius is 5. It's being filled with ice cream at a rate of 3 cubic centimeters per second. Let's start with that number, 3 cubic centimeters per second, and it's being filled, which means it's positive. Cubic centimeters is the volume, and so this is going to go in right here, so that'll be a 3. Pi times 2, the radius, well, we can see that the radius is 5 centimeters. Okay, dr dt is how much the radius changes. So remember, this thing is getting filled with ice cream from the bottom up. We're just putting layer and layer and layer about ice cream. The thing is that the radius never changes the whole time. It stays the same no matter if you're at the bottom or at the top. So that's a value of 0. And then the height. Okay, question for you then about the height. There are 2 numbers for height here. There's a 20 centimeters and a 12 centimeters. Both of those are representing the height. Which one do you use? The 20 represents the container empty. The 12 represents how much ice cream is in there. So when it comes time to use h, we need the 12 for the ice cream. We don't need the 20. The 20 is an empty container. We only want the part that's filled. So we're going to use a 12. Then we also have a pi. We have our r squared, which is still 5. And then dh dt is what we are going to use to answer the question, because the question is how fast is the depth, and depth being the h and the depth changing being the dt. So that's what we'll be looking for to answer our question. So let's simplify. The 0 is going to knock out this entire portion. So I'm left with 3 equals 25 pi times dh over dt. And we just need to get the dh dt alone, so this is a lot easier than the last problem we did. 3 over 25 pi. And that doesn't reduce because 3 and 25 don't have any common factors. The units on this, the height and the time, are measured by centimeters, and the time is measured by seconds. Okay, last question. Here's a street light that's shining and making a shadow for a woman. So the light is behind the person, and she's forming a shadow as she's walking away. A lot of numbers again on here, but we need to focus on the geometry. What we have going on here is a triangle within a triangle. So we have one big right triangle, and then inside of that we have a smaller right triangle. So this is a triangle within a triangle. These are called similar triangles. So that's geometry that you got to remember too. So the way similar triangles work is the proportions of the big triangle to the small triangle. So let's say that the big triangle has height capital H. Well, then the little triangle has height lower case h, and those two are in proportion to each other. So we could say big H in proportion or ratio to little h. Now we have the bases. So we have the base of the little triangle, and then we have the base of the big triangle. And the base of the big triangle we might call B, but it's really this value of x put together with the value of b. So it's better to call that x plus b. So when we set up our proportion, you could use capital B is the base and little b, but it would really be better to use the x plus the little b. Okay, Okay, and so that's our geometry setup. We'll want to cross multiply this geometry here. So we're going to have capital H times lower b, and then we'll have little h times x and little h times b. Then we're ready, so our geometry's done. Then we're ready for our calculus. All right, so our calculus is going to be some product rules here. So the product rule would say, okay, dh over dt with regular b, leave little b alone, and then h times db dt. And then the next product rule would be dh dt times x, and then h times dx dt. And then the last product rule would be dh dt times little b, and then finally little h times db dt. So we've got a lot of calculus going on there. Now we're ready to think about all of these different things. So let's just look at them one by one. Let's look at dh dt. Capital H is the light post, the lamp post, and dh dt is the lamp post moving. Well, the lamp post is not moving. It's not changing height. It's not changing position. And so the value of this is 0, which basically knocks out b, and I don't need it anymore. Let's look at the next rate. Okay, I'm going to look just at the rates right now. Little b dt, well, little b is the shadow, and so that is the rate of the shadow itself, which is what the question is asking me about, so I don't know that yet. We know it's changing, so it's not 0, but we know that, we don't know it yet. The next rate, d little h dt, that's the woman, and that's the changing of her height. Okay, now I know the woman is moving, but is her height changing? Her position, her feet are changing, but her height is not changing. She is still the same 5-foot tall woman she has been the whole time. And so that value is also 0, which is going to wipe out the x. Which means this one right here is also 0, which is going to wipe out the b. Okay, dx dt. X is the way the woman is walking, and she's walking away from the street light. And we finally do have a number for that, and that is 4 feet per second for how the woman is walking. So we finally have something we can put in, that we can put in 4 right there. So we didn't know this one. And then this dB dt is also an unknown. That's the same thing as the other one. So we finally have a 4 we can put in. So let's erase what's gone, and let's simplify what we've got. We've got h, and we have dB dt, and then we have little h, and we have 4, and then we have little h, and we have dB dt. Okay, that's what's left. Now we've got capital H and little h. Capital H is the value of the street light, which is 20, which is not changing at all. And little h is the woman's height, that's 5.5, and that's not going to change anymore either. And now we're ready to solve this. Now I've got a dB dt on both sides. I've got one over here and one over here. That's what are called like terms. So we can subtract 5.5 dB dt from both sides. That's going to be 14.5. Excuse me. dB dt. And then equal to, and then I'm going to multiply 5.5 and 4 together. That's going to give me 22. And then I can divide both sides by 14.5. So dB dt is 22 divided by 14.5, which is 1.517. And that I can put some units on because B, remember, is the shadow. The shadow is measured in feet and the time is measured in seconds. So I tried to show you a little bit of everything you're going to see in your homework. You're going to see a similar triangle question. You are going to see a cylinder question. You're going to see a trig question. And you might see a Pythagorean theorem question. So I tried to give you a little bit of everything that you might see. So refer back to the notes or the video if you need some help. Sign up for a Friday time slot if this is really kicking your butt here and you're having a hard time with it. I'd love to spend a little bit more time one-on-one or one-on-two in a small group with you. Okay, otherwise have a great weekend and enjoy the long holiday, and I will see you next week on Tuesday.